Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If you have a question, we encourage you to ask it using the question feature located on the webinar interface. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we'll be sending out a brief survey following the webinar to get your feedback. Today's presentation will share a state regulator's perspective on PFAS in Minnesota. With that, I'd like to introduce our presenters for today. We're pleased to have with us today Jenny Yingling, Senior Hydrogeologist at the Environmental Health Division of the Minnesota Department of Health. Jenny Yingling works with a team of health risk assessors to evaluate human exposures to harmful chemicals in drinking water related to man-made contaminated sites. Since 2003, she has been the agency's lead investigator of PFAS. She has over 25 years of experience working on contaminated sites and is also the co-chair of the Interstate Technology and Regulatory Council's PFAS team, a group of over 390 environmental professionals drawn from state and federal agencies, academia, industry, consulting, and public interest groups. We're also pleased to have with us today Scott Wilson, President and CEO of Regenesis. Scott Wilson has extensive experience in the development and application of advanced technologies for groundwater and soil restoration. He's a widely published expert with over 30 years experience designing, installing, and operating a broad range of remediation technologies. He has expertise in project management and has directed the successful completion of large industrial remediation programs under state and federal regulatory frameworks. At Regenesis, on specific projects, he plays an active role in technical oversight and program management to ensure conformance with customer expectations. All right, so that concludes my introduction. Now I will hand things over to Scott Wilson to get us started.
Well, thank you, Dane. And again, we're really excited to have Jenny Yingling here to speak with us. Ahead of her presentation, I was asked to give a brief update on Plumestop, our colloidal activated carbon technology, and its adoption in the elimination of PFAS risk within the remediation market. And what we're seeing is that the Plumestop technology is being widely applied now for PFAS sites where it's used to eliminate the risk to downgradient receptors. So let me just dive right into it and give you an update. Okay, about Plumestop. So liquid activated carbon. What we have here is we have a suspension of carbon that we've milled to the size of a red blood cell, about 1 to 2 microns, and it's a colloid, so we call it a colloidal activated carbon. And this activated carbon is suspended in water with a polymer, and a polymer is actually a negatively charged long polymer that wraps around each one of these 1 to 2 micron sized particles, and the negative charges on the outside actually keep it in suspension. It repels each particle from agglomerating with the next. So it looks like black ink. You put it in the subsurface and it'll distribute widely under low pressure, and a single application is cost effective, and as we'll talk about later, it can last for decades. To give you an idea of what it actually looks like in the subsurface, here's a scanning electron micrograph, an image of a sand particle before Plumestop's applied. And if you look at the scale at the bottom, you'll see it's about a 50 micron bar there. So after Plumestop's applied, you actually see this coating on the particle, and then we've moved the scale into about a 20 micron scale here. You'll see that each of those little particles is about 1 to 2 microns. So what we've done is by flowing the Plumestop through the sand, you've converted the sand surfaces, those facies, if you wanted the mineral itself, you converted that into a carbon filter. So the water flowing through here bumps into the carbon and the contaminant's stripped out. So how does it work? Again, the activated carbon coats the aquifer matrix, and it provides extremely fast access to sorption sites because it's only 2 microns in size as opposed to granular activated carbon. And if you're interested in the actual kinetics of it, we'd be glad to get you some information on that by third parties, where it shows that the smaller particles offer much faster reaction and sorption than larger particles such as granular activated carbon or powdered activated carbon. And once you flow this into the subsurface, it converts that underlying geology into a purifying filter. So as the plume migrates, contaminants are sorbed, and as the groundwater passes through that zone. Okay, so here's a graphic interpretation of the subsurface. This is a cross section through a site where we have flux zones, and you'll see the flux zones are those areas of higher permeability where the majority of the water is moving. And here you have 2 flux zones denoted by the red color, the reddish color. And that reddish color shows contamination within that flux zone. It's migrating from the left to the right. And you'll see on the right, there's a monitoring well that's been put in place, and you see that there's contamination showing up in that. In this case, the flux zones are denoted by the dots, which represent sand. But there's also the gray surrounding material, and that would be a silt or a clay. Now, as many of you are aware, that silts and clays very often have very high water content. You can't move that water very easily through the clay or silt, but it inherently is a lot of water in it. That actually is what we call an immobile porosity, because the water in there isn't mobile, but it can store contamination. And if a contamination gradient is set up where contaminants from a higher concentration can move to the lower concentration, they certainly will. And in this case, you get a driving force taking contamination from the flux zone where there's high concentrations to the lower concentrations in the immobile porosity. So let's take a look at and see what happens over time here as this moves forward. So here you have the contamination moving through the flux zone from the left to the right, and you see contamination migrating out into the immobile porosity. That's forward diffusion. What we do is we come in, and if you install Plumestop, the Plumestop will migrate out into the flux zone and settle in, permanently converting the subsurface into a sorptive filter with a 1 to 2 micron layer of carbon. And it does not stop flow or block permeability. We call this the Plumestop treatment zone. And you'll note at the upward gradient, the up gradient side of the flux zone, that there you still have contamination migrating into the Plumestop. And down gradient of the Plumestop, all of the contamination has been taken out of the groundwater, and you have clean water exiting. Now, once you have clean water exiting and you have clean water being generated by the sorption of the Plumestop, you'll start to see back diffusion. That is the contamination moving back out of the immobile porosity and into the flux zone. Well, within the Plumestop area, all of that back diffusion is captured, and you see nothing moving out. There is some back diffusion still occurring outside of the flux zone, outside of the Plumestop zone, and you will pick up a small amount there. But where the Plumestop exists, you have all of the back diffusion captured and clean water exiting the Plumestop zone. So now you've seen how Plumestop can actually stop contamination from migrating. You see PFAS material is now locked up onto the Plumestop area, and if it's at the toe of the plume, there's no back diffusion at all. If there is back diffusion, it's caught by the Plumestop. And you see nothing coming out at the back in your monitoring well. So let's focus now on the impact of that. What's happening here? By locking up the Plumestop, you've actually eliminated the risk of the PFAS. And I want to take people, some of you may have heard me tell this story before, but back in the mid-'80s, there was a medical doctor that left his practice in Portland, Maine, by the name of Frank Lawrence. And Frank Lawrence left his practice to become the first environmental risk assessor and risk assessment company, ELD, Envirologic Data, was formed. And he would go around the nation speaking to regulators and PRPs about risk and what environmental risk really is and how to stop it. And he's the one that showed that risk is equal to hazard times exposure. And I remember vividly sitting in a room full of regulators when Frank said, can you ever imagine having a 3-year-old child stand within 10 feet of a man-eating tiger? And the room just kind of went silent. And then Frank said, it happens thousands of times every day at zoos around the world. The tiger is a snarling environmental hazard, but there's no risk because there's 6 inches of safety glass between the tiger and the 3-year-old child. There's no potential for exposure, therefore there's no risk to that child. Similarly, when we're in groundwater, if we can stop the exposure, we've eliminated the risk. Plumestop binds up the PFAS in situ. It binds it up within that zone. It eliminates the potential for downgradient exposure. Therefore, by eliminating the potential for downgradient exposure, you've eliminated the risk. And that's what we're doing at sites around the world by having zones within the flux zone, zones of Plumestop binding up the contamination and eliminating the exposure downgraded, thereby eliminating the risk. So the next question that's generally asked is, well, but how long is it going to last? Carbon sites get full, the carbon sorption sites get full, and eventually it's going to break through. And that's true. However, the longevity of Plumestop is rated in terms of decades. A single injection of Plumestop into the subsurface will bind PFOA and PFAS for decades. And this was actually the subject of a previous webinar. We don't have time to go into it right now, but I encourage you to go to the Regenesis website and download the Plumestop Longevity for In Situ PFAS Plume Treatment webinar. And in this webinar, Dr. Grant Carey, who's with a company called Pour Water Solutions, he's a recognized, truly recognized expert, internationally recognized on groundwater movement and contaminant transport and the modeling of such. And he's actually modeled sites and displayed that Plumestop will actually bind up PFAS contaminants for decades at a time, and a single injection of Plumestop will in some cases last 5-7 decades, depending on the concentrations and depending on the site-specific conditions. He actually modeled a site where Rick McGregor with In Situ Remediation Limited out of Ontario injected Plumestop on a site unbeknownst to us, and he modeled that with this is Grant Carey modeled it with Rick McGregor and showed that in fact we would have 3 to 7 decades of treatment with a single injection. Now this is all dependent on site characteristics and the exact site-specific isotherms. Dr. Carey is also working with University of Waterloo and University of Carleton University in developing isotherms specific to Plumestop and site conditions and showing decades of longevity with a single application. So the advantages of Plumestop treatment, highly effective at eliminating the risk of PFAS in situ. Concentrations drop dramatically upon injection, depending on how close your monitoring well is to that zone, as we just discussed. It can be within a month, you'll see it drop to non-detect. If it's a distance away, if your monitoring well is a distance from the actual application site, you may have to wait for the groundwater travel time and the back diffusion. However, certainly within a matter of months, you'd see down to below regulatory levels. It's very cost effective. At this specific site that I just mentioned that Rick McGregor injected in the subsurface up in Canada, the total cost of that was a very small site. The total cost of that was $73,000 for the design and application. If you had done pump and treat on that site, the estimates are about $150,000 worth of design and installation, and then $60,000 a year. And as I said, it's estimated the Plumestop will last some 50 years at this site, but let's say it only lasted 20 years. To run that pump and treat system for 20 years would cost you $1.23 million versus the $1.3 million versus the $73,000 that the Plumestop costs. So it's a savings of 1.23 million. So that gives you an idea of the scale of savings by keeping the treatment in situ instead of pumping and treating to the surface and having those O&M costs. The other thing that's really important to understand is that when you pump and treat PFAS, you generate a waste that has to be handled. Whether it's ion exchange resin that has to be regenerated or disposed of, or carbon that has to be regenerated and disposed of, you have PFAS waste to handle. And landfilling is becoming very limited for PFAS waste. And in some countries, it's now banned. So incineration then is the only option. And I don't know if you're aware of it, but incineration is now in question. There was some research done by Bennington College on a major incinerator in New York, and the professor and his graduate students showed that, in fact, it appears that the incineration of PFAS is incomplete, and that there's incomplete combustion products raining down on the soils around the plant. And this is not dissimilar to what we saw in the 90s with PCB incineration, where we thought incinerating PCBs was a solution until we found that thermal destruction was incomplete and we generated dioxins. So right now, thermal destruction is in question. So by using Plumestop in situ, you're eliminating the risk of the PFAS and you're generating no waste in the process. So let's look at how it's being adopted into the marketplace, the use of PFAS. Here's a map of the world focusing with a breakout for the US there. Where we are today is currently there's been 16 project sites treated with PFAS to date. So that means that these sites are ongoing. We are eliminating the risk of PFAS on 16 project sites around the world right now. Another 4 applications are scheduled for the coming quarter. So that puts us at about 20, but it's growing geometrically. People are becoming aware of the fact that they can treat and eliminate the risk in situ. And so what we're seeing is we have another 94 projects right now in final design or regulatory review around the world. There's a hotbed of this in Europe now, as well as along the eastern US coast. So we're seeing somewhere in the range of about 114 sites that either have installed or are in the process of installing Plumestop to eliminate the risk of PFAS. So as I say, it's growing exponentially. And the project types range from small manufacturing sites, the smallest ones, all the way up to Department of Defense sites, very large applications, US EPA Superfund site, and major airports. These have all already been injected. We're already treating PFAS on these sites, EPA Superfund defense sites, airports, and manufacturing facilities. And I want to mention that on every one of the sites where we've injected Plumestop to treat PFAS, all of the projects are performing as designed, and with target PFAS compounds below regulatory levels. I also just want to mention to everybody that PFAS isn't just in our world of remediation. I mean, people are well aware of this in the community, and it's now getting congressional attention at the U.S. Congress level. 2 months ago, there was a bill put forth by the House of Representatives. It was actually the Defense Reauthorization Bill, that the NDAA, the National Defense Authorization Act bill, when it was put forth, where there was actually a call for a moratorium on incineration of PFAS, on any PFAS generated from the Department of Defense. Likewise, within the Senate, the appropriations bill that's in draft right now actually requests the Secretary of Defense to utilize commercially available methods to treat groundwater that are both cost-effective, efficacious, including in situ treatments. And this is a nod to the fact that the Department of Defense is not embracing existing technologies that can stop the spread of PFAS and eliminate the risk from PFAS right now, and that they should do so instead of waiting for a new technology to be developed in the future. That they can implement this right now. So that's the Senate speaking in favor of getting onto it and getting PFAS eliminated. So advantages of Plumestop treatment, just in summary, It's proven performance in the field. It's been used on hundreds and hundreds of project sites for different contamination, and now we've seen it's all on the ground, or in the ground rather, for 16 sites for PFAS treatment. It's been corroborated by third-party research at University of Waterloo, Carleton University, and the good work of Dr. Grant Carey at Pore Water Solutions. It's highly effective at eliminating the risk of PFAS in situ. With a single injection, you can get below regulatory levels within a matter of months. And we're now going on 5 years of data at sites with third-party longevity estimated in terms of decades and decades with a single injection. And by the way, if after that injection you start to get breakthrough in 25 years or 30 years, you simply put in another injection and you get another 25 or 30 years of risk eliminated. And it's highly cost effective, as I've shown you. It's a fraction of the cost of pump and treat. So that's a look at oh, I forgot to mention also, and that there's no PFAS waste generated by using Plumestop in situ. So that's a look at the technology, and I really appreciate you joining us for the talk here today. And with that, I'll turn it over to Ginny Yinling, and we'll take some questions at the end. Ginny, over to you.
Thanks, Scott. Well, I wanted to thank Regenesis for this opportunity to talk to you all about what's been happening in Minnesota with PFAS. I think I gave a presentation either a year or 2 years ago, and so it's a nice time for an update. A lot of things have been happening. As some of you may know, we've been working on a large PFAS contamination site just east of St. Paul, what we call the East Metro PFAS contamination sites. The source of the contamination there was a 3M manufacturing plant located on the Mississippi River, which has been manufacturing PFAS since the 1940s. And some of the waste from that plant were disposed of in 3 disposal sites in neighboring communities. In 2004, we detected PFOS and PFOA, the only PFAS we could even test for at the time, in the city wells of Oakdale. And subsequent investigations have determined that we have over 150 square miles of contaminated groundwater and surface water impacting the drinking water supplies of 18 communities, including 8 municipal well systems and over 4,000 wells, 1,350 or more of which have had to be issued drinking water advisories and have carbon filtration or city water provided to them. And so I want to talk a little bit about how we ended up with such a mess. This area of contamination far exceeds anything that we expected based on the initial modeling that was done in 2005 to try and predict where we would expect to find the contamination. And you can see the main part of the plumes seem to be following the areas that are shown in the black hash marking. Those were the predicted trajectories of these plumes emerging out of the 2 northern disposal areas. But the full area or the full extent of contamination is much broader than we had anticipated. And the reason for that is partly because the area where we're working is bounded by 2 major discharge points. The Mississippi River that bounds the southern half of Washington County, both on the west and the southern boundary of that county, and then the St. Croix River, which bounds it to the east. And so we have a groundwater divide shown by this hash mark line that separates the flow on the west side of the county, which is to the southwest to the Mississippi River, and on the east side, southeast towards the St. Croix River. Initially, we had some hope that all the contamination would stay on the west side of that boundary because all the sites are located west of the groundwater divide. But unfortunately, that didn't turn out to be the case. Partly that's due to a network of deeply buried bedrock valleys that don't have much surface expression, but are former major tributaries to the Mississippi River and the St. Croix Valley. They were infilled as the glaciers retreated, but they still act as tributaries, either through coarse fill within the bedrock valleys or through the permeable bedrock along the edges of the valleys, where solution enlargement of fractures and unburdening of the bedrock when it was exposed back in the past has created a more dense network of permeable fracture systems. And so we see flow along those, and you can see how some of the contamination is lined up specifically along those buried valleys. We also have a major system of bedrock faults in the southeastern part of the county. This is a horst with fault blocks that have vertical displacement up to 150 feet, and then subparallel joint sets that are also seeming to control the flow directions. So just a little quick background on where we're at in Minnesota with PFAS in our drinking water. We set very early on some fairly high levels allowed for PFOA and PFOS. As we've learned more about these chemicals along with the rest of the country, you can see our guidance values have dropped dramatically, with some major jumps both in 2007 and then again in 2016, when the EPA issued their lifetime health advisories and the studies related to those numbers. And our further evaluation of those studies, as well as more recent information, has led us to set even lower lower allowable levels for the long chain PFAS, such as PFOA, PFOS, and PFHXS. We also evaluate PFAS as a mixture in drinking water through a calculation called a health risk index that allows us to evaluate health risk due to the mixtures that we almost invariably find when we're looking at people's drinking water. And so currently the guidance values are close to some of the low values being set across the country, a little bit higher than some of the East Coast states have set. So starting in around 2006 through the 2013 period, our work was controlled primarily through a consent order with 3M that held 3M responsible for site investigations and remedial actions at the 3 disposal sites, as well as their own property. It provided partial funding of a state cleanup at a Washington County landfill, and it also provides the funding for our ongoing sampling and treatment of both public and private wells that have been impacted by PFAS, and the treatment needed when those wells exceed our guidance values. Under that consent order, we provided either carbon filtration or city water connections to about 250 private wells in 2 communities, as well as a treatment system for the wells in Oakdale. It also provided funding for some statewide investigations that I'll talk about in a little while, for things like shallow groundwater, AFFF training sites, fish, wastewater treatment plants, and landfills. Basically, it was funding to allow the state to investigate PFAS at non-3M related sites. As part of our investigation and cleanup of both the Washington County landfill and the 3M sites, unfortunately, we didn't have Plumestop at the time, or at least it hadn't yet been identified as a possible treatment option. And so it really was back to the future for our work at these sites. And so it was dig and isolate. Some of the dirt was incinerated because of other contaminants that didn't allow for it to be landfilled, but primarily the both sediments and soils were excavated, were dredged, and then put into containment cells, triple lined with leachate collection. And groundwater at the sites was basically pump and treat response. One of the things we learned over time was that we had the bonus of opening up our primarily anaerobic waste disposal sites, landfills basically. And not knowing it at the time, we later understood that by doing that, we oxidized precursors that we couldn't even analyze for at that time. And so saw a wave of carboxylates leaving the sites during and following those cleanup activities. We have learned that by removing the exposure, the drinking water exposure pathway, we are achieving good results in terms of the exposures for the affected communities. And this graph shows 3 stages of biomonitoring that were completed in the affected communities where with people that we knew had been exposed to both PFOS and PFOA through their drinking water. And you can see the concentrations in their blood levels dropped off at pretty much the predicted rate based on half-life studies once we removed drinking water exposures, which helped us to conclude that drinking water in these affected communities is really the primary exposure route. People are trending down towards the national average. Of course, across the country, everyone has been exposed to a certain level of PFAS, probably through consumer products if their drinking water is not affected. In 2016, I mentioned the EPA issued their lifetime health advisories, which led us to lower our drinking water numbers over several years, which expanded our investigation area and the number of wells with drinking water advisories. We've also improved our analytical method to achieve lower detection limits, which also expanded the area that we found to be impacted. And so in 2018, we got another input of funding to help us with this work through the settlement with 3M of a natural resource damages litigation. That primarily is funding clean drinking water for both public and private systems, as well as evaluating a surface water pathway with a secondary goal of doing some natural resource restoration. So at this point, this is the impacts that we've identified from PFOS and PFOA in the East Metro. You can see PFOS is largely confined to either on-site at the disposal facilities, but also fairly widespread in the northern part of the affected area, and I'll get into that in just a minute. Whereas PFOA is much more widespread, and this is probably due to a change in the chemistry that was being manufactured at the Cottage Grove facility. The earliest disposal site was the one in Oakdale, so it received both sulfonates and carboxylates, whereas the later chemistry and the waste disposal associated with the Washington County landfill and the Woodbury site was focused more on carboxylate chemistries, and so that the PFOA and other carboxylates appear to be much more widespread throughout the area. Again, we've got the groundwater divide that should have helped us keep the contamination in the western half of the county. But we've learned over time that the high persistence and mobility of PFAS means that once it enters a surface water system, it can be transported long distances and impact groundwater at isolated areas far removed from the original source area. We learned this because of the difference in the chemistries in the Oakdale site and the Washington County landfill. And you can see here, groundwater flow is illustrated by the light blue arrows, and surface water or stormwater runoff is shown with the dark blue arrows. The Oakdale disposal site is in a large wetland complex that's drained by a stream that flows eastward towards the city of Lake Elmo. And as it moves to the east, it becomes a losing stream, and much of the year is a dry creek bed because the base flow is infiltrating through the stream bed and back down to the groundwater. So all along its course, we have infiltration back into neighborhoods that are supplied by private wells and had many hundreds of wells impacted by that. It also flowed through a stormwater control system that was installed in the late 80s to early 90s to transport excess stormwater runoff out to the St. Croix River. And so that's illustrated by the dark blue arrows that are shown trending east into the river. But a large part of that stormwater system includes use of ditches, ponds, and stormwater retention ponds, all of which infiltrate rapidly to the groundwater, because in this area, the bedrock is either outcropping or as little as 30 feet below those stormwater ponds. And so you can see from the light blue arrows and the shape of the plume, these high concentration areas migrating away from each of the individual stormwater ponds. And then you can also see how the plume is tracking along some of those buried valleys that I showed earlier. So it's an important reminder when we're working at our sites that groundwater is a major pathway, but surface water can really complicate your understanding of how your contaminants are migrating, because the surface water can transport across groundwater divides, as it did in this portion of our plume, and then re-infiltrate and create discrete groundwater contamination zones miles from the actual source area. And we've seen this at other sites as well. I already mentioned the 2018 settlement with 3M that has provided additional funding to do the work. That work is ongoing, especially the portion trying to identify the best options for providing clean water to these communities. There's been a long, almost 2-year process now of community participation to evaluate what are the best either treatment options or other systems for providing clean drinking water and expanding the city water systems to include more people. That we hope to see wrapped up in the next few months, and then plans start to be developed for installation of those expanded drinking water supply systems to areas currently getting their water from private wells that are highly impacted and are on carbon filtration systems, which is not a good long-term solution for people, and very expensive for managing into the future. So part of the settlement was focused not only on providing clean water to the cities and to the private well owners, but also for evaluation of that surface water pathway and hopefully restoration of it so that it stops being an ongoing release to the environment for the PFAS. And we hope that this will provide some opportunities for innovation along the lines that Scott was discussing, and maybe some other opportunities as well. One thing that the state is currently looking at for that surface water is foam fractionation, and whether that's a way to remove some of the contamination from that system. We do know we have foam showing up on 2 of the surface water systems that have been impacted by the sites, and the concentrations in that foam is many orders of magnitude higher than what we actually detect in the water because of the high affinity of PFAS, especially PFOS, for the air-water interface. So that's the work that we've been doing in the East Metro, and a quick update for you on that. I wanted to also talk about what we're doing statewide, because like other states, we are now trying to get our arms around the extent of this problem and how to identify sources and conduits that are causing release of PFAS into the environment, and then trying to prioritize those for actions. Of course, like most states, our initial primary focus has been on AFFF sites where we find high concentrations of PFAS. We did some work early on in 2008 with some of the funding that was made available through the consent agreement with 3M, and sampled sites across the state that did identify one site, the Bemidji Airport, that I'll talk about in a little more detail in a second. But it also helped us to understand that the primary releases are occurring at larger uses, not the municipal fire training sites that are maybe once a year with a small volume of foam, but the training, the larger training areas, Department of Defense sites, and some of our training academies, refineries, and airports. We also have identified through a site investigation the Duluth Airport, and I'm sorry, that's the one I'm actually going to talk about. And we're in the process of evaluating some Army National Guard bases over the next couple of years. The reason I want to talk about the Duluth Airport and Air National Guard base is because, again, surface water has appears to be playing a major role in the transport of the contaminants. The purple dots, tiny purple dots that you see down near the lower right-hand corner of this map are the fire training areas at the airport and the Air National Guard base. They were investigated and cleaned up for other contaminants several decades ago, but subsequent investigations have shown high levels of PFAS associated with those. And you can see the blue lines that illustrate the network of surface water systems near the site. There's a drainage system that passes through the wetlands north of the airport and into a lake to the north of the airport, Wild Rice Lake. And that surface water, those ditches and streams are carrying a heavy load of PFAS, especially that western ditch. We also have a major creek, Miller Creek, which runs from just to the northeast of the airport, across the southeastern edge of the airport, and then south, and then it trends to the east out to the St. Louis estuary and into Lake Superior. It also has high levels of PFAS in it downstream of the airport. What we've observed as we've been sampling private wells, which are shown by the green dots, is that the distribution of contamination, including 2 wells with that are shown in yellow where we've issued advisories, the distribution doesn't really follow with the groundwater flow direction. They seem to be clustered near the creeks. And so sampling of those surface waters is what helped us to identify those as the major pathway for the movement of the PFAS. And then fish sampling in both Wild Rice Lake and Fish Lake further to the northwest has detected elevated levels of PFOS in the fish in those lakes. And we can still detect the impact of the PFAS from this site all the way up into Fish Lake, as much as 8 miles from the original source area. So again, surface water systems are a primary concern for us in an area with such shallow groundwater and the potential for migration of the PFAS through away from our sites. Other investigations done early on with our funding through the consent agreement included chrome plating, which we initially identified because of fish sampling that led us back through the water system, either wastewater or surface water, and to chrome platers, with interestingly release patterns that were not only to the sanitary sewer, but also vent releases from one chrome plater that led to runoff from their roof and then infiltration to the groundwater and runoff into the surface water. We also have a lot of work going on in the state, and I'm going to go through this pretty quickly. Of course, community water systems have been a major focus for us, not only through the UCMR3, but a subsequent sampling effort here in the state in 2019 that looked at an additional 46 systems. 13 systems have ongoing sampling for systems that are located near the known PFAS sites. We also have an EPA grant that we'll be using to sample an additional 125 public systems, looking at somewhat of a semi-random selection, but also at the most vulnerable systems, and using an expanded analyte list compared to what we've used in the past. And of course, UCMR5 is expected to include PFAS, but that's still several years out. I believe that will be in 2023 to 2025. I may have my dates wrong on that one. We've also done quite a bit of shallow groundwater sampling starting in 2008 not good detection limits back then, so we've redone that work and found that 70% of our tested wells contain PFAS, primarily PFBA, but you can also see we had a number of wells that exceeded our guidance values for PFOA or PFOS. If there's any good news, we did see declining concentrations of PFAS in wells that have been sampled multiple times between 2013 and 2017, likely due to the phase out of the PFAS and PFOA chemistries here in the US. In Minnesota, we protect our surface waters for multiple uses, and our main concern to date has been accumulation of PFAS, especially PFOS in fish. So we've been looking at that across the state. We've tested 95% of the waterways we've tested had at least one fish with detectable PFOS. And you can see we've got 10 water bodies with impairments based on fish consumption advice of no more than 1 meal per month or less. We have one lake where we've advised people not to eat any fish. Moving along, we do have a lot of next steps in regards to surface water, including additional fish sampling, but also the DNR this fall has been collecting deer organ meats, liver and kidney for deer harvested near sites with known PFAS in the surface waters to see if there's any risk of exposure to hunters who are using those organs for food. And we hope to improve our understanding of bioaccumulation and determine whether we need a statewide water quality standard for PFOS in fish tissue. And so there's still a lot of work going on, including work on risk assessment for PFAS foam and evaluating risks to aquatic life and wildlife that drink from surface waters. The state, through the Minnesota Pollution Control Agency, is also trying to evaluate PFAS sources and the conduits that are channeling PFAS into the environment. And so they are working a pilot project to try and develop a tool to identify and prioritize potential PFAS sources using the NAICS code to identify which industries may be using PFAS in their processes, and then trying to prioritize those that are closest to drinking water and surface waters. The work to validate that protocol has been delayed, of course, because of some of the COVID response here in Minnesota, but we hope to see that proceeding in the next year or so. We've also done a lot of work looking at the conduits for PFAS, the many sources in consumer products that then pass through both our landfills, where we've been finding PFAS in 97% of those sampled, as well as landfill leachate, which can have very high levels of PFAS, and then looking at various alternatives for managing that leachate, including thermal evaporators and various electrochemical treatments to try and remove the PFAS from the leachate before it can go for further treatment. We've also identified that runoff from our compost sites that not only collect yard waste, but also consumer products such as food, compostable food packaging and serviceware, has concentrated PFAS in that runoff from the compost sites, which they are required to collect. So work is ongoing to try to determine what are the sources to those compost facilities and how to manage that. And finally, of course, wastewater treatment plants are also a pass-through system where PFAS enters our surface waters. And so work is ongoing to look at how do we manage both the effluent and the biosolids from those facilities. We have a number of bills that were introduced this last session that are still live, and as well as work ongoing at the Pollution Control Agency and the Health Department to identify regulatory gaps that may be that we may be able to address, both in terms of products as well as risk assessment and treatment. So we've learned a lot of lessons over the years that drinking water is a major exposure pathway. I think I moved a little too quickly there. That we're constantly being surprised by where PFAS will end up in the environment and how it gets there. That surface water is playing a major role at many of our sites, and that our remedial actions are having unintended consequences that we have to try to anticipate and be ready for in terms of monitoring and treatment. And as we move into use of the new EPA method that includes PFBA, we should expect to start finding that extremely soluble PFAS in most of the sites where we're looking for them. And we also have a lot of things that we still need to evaluate and then prioritize for investigation and treatment to protect people and the environment. So I'm going to leave it there and turn it back over to our moderator for the question and answer period.
All right, thank you, Jenny. That concludes the formal section of our presentation. So at this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, just a couple of quick reminders. First, you will receive a follow-up email with a brief survey. We really appreciate your feedback, so please take a minute to let us know how we did. Also, after the webinar, you'll receive a link to the recording as soon as it is available. All right, so let's circle back to the questions here. We have a question. This one is for Ginny, and it is, have you seen any health effects in the exposed population near the 3M sites?
Yeah, so we've done a number of looks at the available health data for people in those affected communities. We looked at our cancer surveillance data, did not see increases in the types of cancers that have been associated with PFAS. There was some indication from the 3M worker studies that there may be slight increases in some cancers in the workers who work on the production lines and who obviously have much higher levels of exposure than we've seen in the drinking water in the affected communities. We've had reports from people in the areas that were most highly affected by the releases that of cancer cases, but there's nothing that shows up in our cancer or birth outcomes data that suggests that we've had any population-wide impacts. That's not to say that we don't think there have been health effects to the people who were most highly exposed, either from private wells closest to the source areas or to some of the people using the city water systems that were most impacted, particularly the Oakdale system. We just don't see it showing when we look at the broader population in that area.
Okay. All right, so here's another question. This one is for Scott. And the question is, you mentioned injection into flux zones. So how do you go about identifying those zones?
Yeah, so the flux zones are just those zones of higher permeability in the subsurface that they're taking most of the contaminant flow. And they can be identified by any number of the high resolution type techniques, MIP or hydrologic profiling tool. They'll both aid in that. Another great approach is the use of flux samplers. There's actually tools that can go down the well that'll sample the flux and give you an idea of both groundwater flow rate as well as contaminant flow rate. There's a group called EnviroFlux out of Florida. Professor Mike Annabelle put that together years ago in that technology. There's also a group called iFlux out of Belgium that have tools sort of like that that do this similar. And we've developed an advanced version of that, but it's in limited supply now. But we have a tool that we use as well. So it actually can measure the flux and give you an idea of where that flux zone exists in the subsurface and what's the highest rate of flow vertically.
All right, thank you, Scott. So these are some questions for Ginny related to federal regulations. And they are, do you see the possibility of an MCL with the incoming Biden administration? And what do you see happening at the federal level? Will these chemicals be listed as hazardous waste under RCRA?
Yeah, so, you know, we've not heard anything yet from the incoming administration specific to PFAS, but I am optimistic that we'll see the EPA take up the consideration of MCLs a little more quickly now with hopefully support from this new administration. The MCLs themselves may not be that important to a lot of states who have already set their own guidance values or their own MCLs that are lower than what EPA is considering. They're looking towards the 70 nanograms per liter combined for PFOS and PFOA as the likely MCLs. And a lot of us are already well below that in terms of what we're applying in our states. But the value of having an MCL is both for states that currently have not been able to set their own guidance values, but more importantly for federal sites to be able to proceed. They need some guidance values to be applied or that they can apply to those sites. So the MCLs can play a critical role for a number of reasons. The listing as a hazardous substance or hazardous waste under RCRA is also a critical component to the federal picture because Department of Defense sites and other federal sites, they've done investigations, they've done some cleanups where drinking water or other resources are contaminated above promulgated state values. But in order for them to really get going on site cleanups, they need federal listing as hazardous substances in order for them to be able to expend cleanup dollars at those sites. And as the Duluth Air National Guard site illustrated, we've got lots of investigation going on. We don't have a lot of cleanup activities there. And we really need to cut off the contaminant transport to those surface waters to protect people both for drinking water and fish consumption reasons. But because our PFHXS value is not promulgated, it is not considered a value that the federal agencies or the Department of Defense can use in determining whether they will do a cleanup action. And so we're kind of caught in this trap between state and federal numbers. So we're very anxious to see these chemicals be listed as hazardous substances under RCRA.
Okay, thank you, Jenny. So here's another question. This one is for Scott, and it is regarding treating back diffusion. What data do you have on this?
Yeah, so the ability of Plumestop to treat back diffusion, it's well documented in the number of sites that have been accomplished. On every site that we've injected Plumestop on, you see concentrations drop dramatically below what you would expect to see from a pumping system, let's say. So usually when pump and treat systems are maintained for a while, you reach an asymptote where the high concentrations of recovery, contaminant recovery, drop off, but the concentrations that you're receiving are still above regulatory standards. If you actually inject Plumestop, you see that drop off to non-detect, and that's because that contamination that's moving out from the immobile porosity into the flux zone is actually caught by the Plumestop. So we've seen this on sites throughout the world with Plumestop injected, but there's also been some very controlled third-party lab experiments. In fact, the most notable is the work done at Colorado State in Professor Tom Sales' lab, where they had generated a dual porosity sand tank where they had sands and silts interspersed in layers, and it was under an ESTCP sort of funding process where they looked at all different types of technologies to stop back diffusion. Nothing seemed to work, be it bio or chemical oxidation, iron, etc. They then came back, we came back and funded the exact same experiments, exact same tanks with the same people. And with Plumestop, it was clear that, in fact, the back diffusion that was happening from the silts and silt clay zone was completely removed by the Plumestop residing in the flux zones. So, yeah, there's evidence both in terms of practical anecdotal evidence from the field, but there's also controlled laboratory experiments from third-party labs.
Okay, thank you, Scott. So here's another question. This one is for Ginny. It is, are you considering which PFAS treatment options are viable in the state of Minnesota?
Yeah, so currently, I think you could see from my presentation, right now we're really pretty much restricted to using carbon filtration for contaminated water, and we've been doing primarily excavation and either incineration or containment for contaminated soils and sediments. None of those are satisfying. Pump and treat, as Scott showed so well on his one slide, is so much more expensive and so fruitless, really, in the long run, that we do hope we're going to start seeing application of some additional technologies. I'm hoping that through the work that's being done in the East Metro under this settlement grant from the litigation, that we'll see some new technologies being applied. We are seeing pilot testing of ion exchange resins for municipal systems. That's not currently permitted in the state of Minnesota for use on community systems, but we're very eager to see the results and go through the process to give cities additional options for how they treat their water. And the ion exchange resin studies that have, or projects that have been implemented around the world seem to suggest it's probably a better solution when you have mixtures of PFAS that include some of the short chain molecules that don't absorb as well to granular activated carbon. So I'm hopeful that we will see some applications of new technologies, and I know there's been discussion of whether there are places in the East Metro and at other sites where Plumestop might provide some of our treatment needs for stopping migration off-site. And so I suspect we'll be evaluating that as well as other options for trying to eliminate the discharge from groundwater to surface water, or the infiltration from surface water back to groundwater.
Okay, thanks, Ginny. So we have another question here, and this one is for Scott. And it is, what pressures are used to install Plumestop?
Yeah, so Plumestop is very small particles, smaller than the pore-through diameters of most soils. So the actual carbon particles in Plumestop can migrate even into silts. So you don't need a high pressure. So you can gravity it in down. You can actually just pour it down wells and it'll move out into the aquifer. Or you can inject under low pressure, but there's no need to frack or anything like that because the particles are smaller than the pore-through diameters it's moving through. Yeah, thanks.
All right, thank you very much, Ginny, and thank you, Scott. That is going to be the end of our chat questions. If we did not get to your questions, someone will make an effort to follow up with you. If you'd like to learn more about remediation solutions from Regenesis, please visit regenesis.com. Thanks again very much to Ginny Yingling and to Scott Wilson, and thanks to everyone who could join us. Have a great day.